Hello everyone, welcome to my presentation. My name is Chuanyu. Today I will present our work, KeepON, supporting deterministic traffic on standard NICs. So this work was done during my PhD at UConn in collaboration with University of Iowa and NASA Johnson Space Center. So in short, in this paper, we solved the last inch problem of TSN when integrated with the commodity end stations. So we designed a traffic scheduling mechanism using just a standardized NIC. So we also built a prototype based on the Raspberry Pi, which is available on our GitHub. So I'll start with the background. So today, the mission-critical applications like autonomous vehicles, spacecraft, and smart factories, they are typically also the networked system. So they include many sensors, actuators, and controllers. And those devices, they are all interconnected by a communication network. And in those mission-critical systems, the correctness depends on both data correctness and timing correctness. So for the timing correctness, specifically, the network packet must arrive with bounded latency and bounded jitter. So on the left, we show a system has a good average latency, but it has a long tail. So that means some packets takes much longer time to arrive. So that may be fine for the general system, but is risky for the real-time system. And on the right, we show that the average is slightly higher, but there's no long tail. So the latency and jitter is tightly bounded and predictable. So this is required by the real-time system. So to achieve the deterministic communication, the traditional solution is using domain-specific system, like those CAN bus. So each domain is connected by a dedicated layer of keyballs. So this way, you can get a extremely reliable packet delivery, but it's also expensive and with high keyball complexity and fundamentally have very low bandwidth. So the industry is now moving towards a converged architecture, which aims to replace those domain-specific bus with a single Ethernet backbone. But however, the standard Ethernet is designed as best effort, which can introduce the large jitter when multiple traffics wants to pass the same switch at the same time. So it can cause the random queuing delay. So that's why the time-sensitive networking, the TSN, is designed to solve this by two features. The first one is the network-wide synchronization. So that means every switch and the end stations in the network, they all share a common clock. And the second one is the time-aware scheduling. So based on those clocks, so each switch will follow a global schedule and knows exactly when to forward which packet. And because for each packet, the entire path is scheduled in advance. So no two traffics will use the same resource at the same time. So there's no random queuing, and the latency is fully deterministic. And if we look at this example on the right, so every colored cell is a reserved transmission time slot, and they are all calculated before running the network. So if we take the green one, the F2 as an example, it's supposed to leave the end station at T2 and start transmission at the first switch at T3, then transmit at next switch at T5. So every switch along the way has a slot waiting exactly for this traffic. But one challenge in TSN is it assumes that end stations are also perfectly deterministic. But in practice, the commodity end stations, they are not deterministic. And this mismatch fundamentally breaks the end-to-end determinism. So if we zoom into the blue region, so it breaks here when the end station introduces jitter. So suppose the end station sends the traffic F2 just a few microseconds late. So F2 will arrive at switch after its reserved slot. So the slot is gone and F2 has to wait for it. And every downstream switch slot for F2 will stay empty. And if it is sent early, it's actually worse because the F2 arrives before the slot opens, so it's sitting in the switch buffer occupying the egress port. So when another traffic, the orange one, F6 arrives, so it gets delayed. So in both cases, a tiny end station jitter can cause the cascading effects to the downstreams and totally mess up the TSN schedule. So why the end station determinism is so hard? Because a network packet must traverse the OS, the memory, and the PCIe bus. And every single stage can inject the random delay, and those random delay can accumulate in the end. So we show the jitter between the packet's scheduled time and their actual release time as the NIC. So the distribution has a long tail, which breaks the TSN's assumption on the end station. And the existing approach to solve this problem is by using hardware scheduling offloading, so which has a hardware scheduler and the PDP timer as the NIC. And the application can set a schedule time when send out packet, and the NIC will hold that packet until that exact moment, and then release it on the wire. Because the cog is on the NIC, so the PCIe jitter and the software jitter in the middle, they don't affect the eventual timing. So this gives us a very high accuracy, but it's not very flexible because this hardware function is not widely supported in those commercial NICs. And it often requires to install the new NIC hardware, which can be expensive, and in some legacy systems, you may not even have a PCIe port to install those new NICs. So to bypass this unbounded delay and PCIe jitter in the software without relying on the hardware functions, we propose KeepON. So the key idea of KeepON is to emulate this hardware cog using some physical network properties. So if we force the NIC to continuously transmit the fixed-sized dummy packets at the physical line rate, then the number of the packet will become a perfect cog tick. So here we show how that works. The first step, we use the polymodal driver to constantly push the same size dummy packets to the NIC. And because the NIC sends at line rate, so there's no gap between each packet. And each packet has the same size. So the DMA run itself becomes a physical timeline. And each slot perfectly represents a precise future time. And then when the application wants to schedule a packet, let's say at T2, so instead of waiting until T2, it can simply find the corresponding future slot and insert the packet right away. And by doing this, we can make sure that packet release time as the NIC will be exactly T2. We will firstly show why this can work. So the key idea relies on the assumption that the NIC can transmit packets with predictable timing at line rate. So here we first validate this by a simple experiment. So we basically just use iPerf to send packets at different utilizations, and we timestamp each packet when they actually leave on the wire. So we see that at 50 and 80 utilizations, the result has a high variance. But at the line rate, the variance drops to 6 nanoseconds, which means at line rate, by the packet index, we can perfectly predict the time when they leave the NIC for each packet. And this observation is consistent on different hardware platforms, so which is not dependent on specific hardware. And another obvious question is, if we keep transmitting at line rate, so will this flood the network? So our second observation shows that it won't hurt the network. So because we construct those dummy packets by intentionally use the corrupted CRC code. And those corrupted packets are immediately detected and dropped by the NIC at the first hop of switch. So this is also a basic Ethernet standard function. And our measurement shows dropping those dummy packets introduce no bandwidth or timing overhead on the receiver side. So based on this key idea, we designed the architecture of KeepON, which has 2 layers. The first layer is the core driver model on the left side. so which aims to achieve deterministic at a single node. That's what we'll focus on today. So it has two components. One is the CP PMD, which keeps the NIC at a line rate, and the scheduling part, which handles the how to construct the clock and the packet scheduling logic. And on top of the core driver, we have two extensions for the end-to-end integration with the TSN network, but we won't cover it in today's presentation. If you're interested, you can check the details in our paper. So the core challenge of KeepON is how do we keep the NIC always on? Because every idle moment will break the line rate property and destroy the timing determinism. So to achieve this, we use a polling mode driver that cycles through 4 steps. The first step, we initialize the DMA run with the dummy packets, which has the wrong CIC code. And second step, we query the consumer index. So we know how many packets the NIC has already transmitted. So we can use this as a timer. And then instead of deallocating the memory for those already transmitted packets, like the traditional DMA run, we reclaim them as the dummy packets by simply overwriting the wrong CRC code. And next step, we advance the producer index. This way, we ensure the producer index is always ahead of the consumer index. And we repeat the step 2, 3, 4. The NIC will never see the run being empty, and the transmission will always keep on. And next, we show how do we construct the hardware clock, PDB clock. Because that line rate property, we can use the number of the transmission as a clock tick. So this gives us a two-way mapping between the time and the run index. The time will equal to the number of the transmission times the transmission time plus the offset. And the offset is to synchronize the ePHC with the clock in the other clocks in the network. And this packet counter can be tracked by the consumer index, as we discussed in the previous slides. And on the other way, we can also map the schedule time to the run index. For example, if you want to, in this example, if you want to schedule at time T6, so assume the system starts at T0, so T6 will be the 6th start. And if you want to schedule further, like in the T10, so because the run will repeat, so you can find the position by mod the run size. So you'll know the T10 is in this position. And for the scheduling logic, when the application schedule, when an application schedule packet, given the schedule time T, so first step, you will use ePHC to calculate the corresponding run index. Then we check if that index is available or not. So it should have the wrong CRC code, which means no packet is scheduled here. And if it's available, we pack the data into the fixed size, and we reset the CRC to be correct. And then we just overwrite the dummy packet at that position. And NIC will send that packet in the future when the consumer index reaches that slot. And here one challenge is the schedule time. It cannot be super far away in the future because the run buffer only has a limited size. So to solve this, we put another dynamic length priority queue before the DMA run to hold the packets from the application based on their schedule time. And we only release them to the queue when it's close to its schedule time. And next, we go to the evaluation. So for the evaluation, we compared KeepON with the hardware-based approach, the IGB, and the standard Linux driver, GNET. So we send a periodic traffic with different periods from 200 microseconds to 1 millisecond. And we check their jitter when they actually sent out on the wire. So from the result, we can say the standard Linux driver, which is the dark bars, it shows a high average jitter of approximately 5 microseconds. And the hardware approach, the IGB, can achieve much better, about 7.7 nanoseconds of scheduling accuracy, so which is much better than the software. And for the KeepON, which operate in the software, so we can achieve the 3.7 nanoseconds jitter, so which is even better than the hardware-based approach about the scheduling accuracy. And one potential concern is if the CPU cost is high when we keep the NIC always on. So in practice, this overhead can be pretty low by fine-tuning the batch size and the slot size of the polling mode driver. So by doing this, we can low down the CPU utilization to under 10%. And finally, to validate KeepON in a realistic setting, we deploy it on the RESI cyber physical testbed, which is a testbed for the research of deep space habitat. So the main challenge in this testbed for the communication system is to integrate those legacy devices which use other protocols like IS-232 or analog signals into the TSN network. So we use the Raspberry Pi as gateway, and we run those critical traffics with both default Linux driver and KeepON. And we run 12 critical flows across the 4 TSN switches with 1 millisecond control period, which reflects the real RESI workload. So we show that with the default Linux driver, the schedule completely breaks. So the delay spikes can go above 1 millisecond, and deadlines are missed. But if we use KeepON with the same hardware, we can achieve sub-microsecond jitter end-to-end and meet every single deadline. So in short, we try to figure out how to achieve deterministic packet transmission without relying on specific hardware. And we try to use some Ethernet, the physical property, with some software design to achieve determinism. Okay, thank you. Happy to take any questions.